Everyone. So today I want to talk about a specific technique that can be used to solve a lot of similar kind of problems on LeetCode. So this is one of the examples. Like I'll go through the basic idea of the technique and why we're doing that. So basically, if you read this question, so what we're supposed to do in this is like they have given four values num1, num2, minsum, and maxim. So we're supposed to count all the numbers which lie between this range and the sum of whose digits is between this range. So ideally, like if you could, the brute force way to do this would be to go through all the numbers between this range and for each number, calculate the digit sum and see if it lies between these two ranges. If it does, then you count it as one of the answers for your question. But where the problem arises and why this is basically a hard question in lead code is if you take a look at the ranges, num1 and num2 can lie anywhere between 1 and 10 to the power 22, which is longer than long value in Java. And going through all the values in this would be not feasible in these kind of questions. So basically, what you're gonna do is like for this range, you're gonna be checking. Suppose num1 is 1 and num2 is 10 power 22. So you're gonna check the whole range, like from 1 to 10 power 22, which is O of n. And for each number, you're gonna calculate if the digit sum is in this range or not. So that would be log n, right? So if you brute force these type of questions, the time complexity would be O of n into log n, right? And for such ranges, that's not feasible. So we need to find something better. Okay, so now we have the idea of the question, what the question is asking. Let's try to like find a better way to do this. So the way to go about this, give me a moment. Yeah. So what the question is asking is, we have a lower range, and we have upper range, right? We need to find all the numbers between these ranges whose digit sum lies between some value min and max. So, for example, if the number was 34297, the digit sum of this will be 25. Yeah, 25. Yeah, so D sum is 25. Now, if the values were, suppose min was 21, max was 42, this would be a legit number, and we would use count this to our answer, right? But as we discussed, so if this upper range is 1 and the lower range is 1, and the upper range is 2, you need to go through all the numbers between this range and find the digit sum. So the pseudocode of a brute force solution would be like for I equal to L, I less than equal to R, or upper as I've named it. So for all these numbers, you need to check whether the digit sum lies between min and max. So suppose we have a count variable, and what we're gonna do is in current number is I, while uh, current is greater than 0. We're gonna find the remainder to check the to get the last digit. The remainder will be modulo 10. We'll get the rightmost, the least significant digit for this, and then we'll add it to a sum, which is the digit sum for this number. So sum equal to 0, uh, equal to sum plus r, and then we reduce the number by 10. And at the end, we check if sum is greater than equal to min, and then sum less than equal to max, you add it to the count, right? So this is the force way of doing this. So this loop here is it takes log n time, right? And this whole thing will be n log n. So the time complexity will be this. And as we discussed, for large ranges, this could go up to 10 power 22, which is not feasible. So we need something better. So what do we do here? So basically, suppose think about individual digits now. Now you have a number 3, 4, 5, 7, 2, right? So now what we're going to do is, instead of going through the entire range, what we're going to do is, like, at each position. So suppose this is position 0, the most significant bit is position 0, then 1, 2, 3, and so on, right? This is the position. So what we're going to do is, we're going to try to like add different digits at each position, and see and try to find a recursive solution of what the counts can be. So for suppose for this example, we're supposed to find count. Uh, this is the position, and this is our current sum. So this will be equal to count of position plus 1 and sum plus the digit at position 0, right? And we need to, so the idea here is, suppose in this number we put 3 here, right? So we've added 3 to our accumulating sum, and then we're checking what digits can be put in these positions. Now, at the end, after you've put 3, you can, for the position 1, you can put 1, 0, 2, 3, and 4. Not anything higher, because if you do that, if you put 5, right? If you put 5 in this position 1, it's gonna make this number, whatever we're getting from this solution, greater than this number, which is above our range, right? Okay, let me scratch that. We're not gonna do it on an individual number, but we're gonna try it on the range. So suppose the range was 3, 3, 7, 8, 9, 5, 4, right? So what we're gonna do is, suppose we put 3 here now. So for the second one, we'll only be able to, this is the upper range. So this is the upper range. For the second position, we can only use the digits 0, 1, 2, 3, not anything higher. Because if we do that, we'll go over our upper range. So if we choose 0, for example, now, doesn't matter what you use in, like, whatever digit you use after this, because the most significant bit is now lower than uh, anything else. So what happened here was, we tried to decide on a number where we used 3 first and put a 0 here. Now, no matter what we put in the rest of the positions, it's gonna be lesser than the upper range. So we, after this, if you've chosen 0, we can use any digits. So 0, 1, 2, 3, 4 till 9, right? If we do put 1, it's again smaller than the second digit in this case. And with the same logic, we can put anything from 0 to 9. Same thing with 2. You can put anything till 10. Now, if in the second position we use 3, now see, so if we've used 3, so anything after that, you need to make sure it's lower than the upper range. And how do you make sure of that? So for the next digit, so if you did use 3, for the next digit, you can't use anything greater than 7. So those so, this like choices here are from 0 to 7, right? If you choose 8, this number that we're generating is gonna be greater than this upper range here, right? So now look at the pattern. So we need something to see if we've in the previous position we've chosen a number equal to or less than the digit at that position. So if now again in this case, if you use anything from 0 to 6, you're good. You're good after like in the subsequent positions, you're good to use anything because now the this bit is smaller than the bit used in the upper range. So you can use anything over here. But if you do use 7, now you're again bound by what you use in this position, right? So we need some variable to see if this is the limit or like if the number is tight, let's say tight, for example. So to find the count from k, where sum with accumulated sum till now, and another variable called tight or anything else you want to call it, the bound or something. So this is what we're trying to find. And in the end, like let's say the base case for this situation would be if so this position you've reached so the number like the upper range was here. This was the upper range, and these were the positions. So if you've reached position 7 now, so you have formed a number in this range lower than this, and you've reached the end of it. So at the end of it, when k equal to num dot length, assuming we've converted that number, the upper range, into a string value, if we've reached this case, we just gonna check if sum is greater than min and sum is less than max. If that's the case, we return 1. So what we're doing here is we're trying to place different digits in each position. So this is the upper range. So like whatever number you choose is gonna be with under this or equal to this. So whatever digit you place in this, we're trying to place different digits. So this in this recursive sense, we're trying to place different digits in each of the positions, which stays under the upper range, and we're calculating sum as we go along. So suppose this is like this will be called with count of 0, which is the position 0, sum 0, and tightness as 1, because in the first case you have no other option other than using something less than 3 in this case. So in the first case you can only take up the digits to 0, 1, 2, and 3. Anything over this you're out of the range. So if you use the digit 4 in the 0th position, you're out of the range. So uh, you can see this is going into a recursive area. So what digit DP does. So that's the whole technique here. It's called digit dynamic programming. So we're trying out different digits in each of the positions, trying to keep everything under the upper range, and at the end calculating the sum. So this is a recursive solution, right? Recursive function. So what are we trying to uh, like use dynamic programming for? So we're trying to see. So suppose, for example, if the position you're trying to place something on was 0th position, and the number was 2543. Okay. So you're trying to calculate if you put 2 here in the first position, in the 0th position, you're trying to put a 2, right? And this is the number we're trying to find. And in the second one, this is another number that exists, right? So in these are all in the ranges. So in the first case, you get sum as 2, right? And if you put 5 in the first in the second case, and then for the next one, uh, at position 1, you put 5 here. You try to place 5 in the second position. So the sum is 7. The digit sum is 7. In the second case, you put 2 here. So the digit sum is again 7. So you see, like some of the states here are going to repeat themselves. So this is what we're trying to memorize or like cache it. So if again this position arises, we know what the answer is. So now let's try to like forget about all this and try to get a recursive recursive formula for this. So count of k, and this is the digit sum, right? And some tightness, like so, as I explained, if you are trying to place a number on this position, you can't place anything over 7, right? So this will tell us if we're in that limit. So if you choose any, so suppose in this case, if you place 2 here, right? So for the next numbers, next positions, you can choose anything. So you're not bound by anything. So in that case, my tight variable will be 0. If we choose 7, so we still need to make sure that we do not go over the range. And in that case, if we do use 7, our tight variable will be 1. So for the next one, we know, okay, this is 1. The tight variable is 1. So we need to make sure we do not go over 0 to 8. Like anything over 0 to 8, and a number will go over the upper range. So we need to find all the numbers which lie within that range and have us min sum, have the digit sum less than max and greater than min. So we're trying to find this, right? So this can be calculated by summation of, so all the digits. So this sum can be this count can be placed by using 0 to 9, like digit 0 to 9 in k plus 1 position, right? So this is nothing but what you place in count of k plus 1, uh, this d sum plus the digit that you use at kth position, right? And the type variable. So if type equal to 1, in that case, I will go from 0 to the digit at upper range of upper range at k. So the idea here is, so if the position was this one and the upper range had 8 in this, so you can only go from 0 to 8. So whatever at position 1 was the digit, you can only go from 0 to that digit, right? And this is the recursive solution. So basically, if it was the tight was 0, you would go from this upper range will become 9. So this is the recursive solution. And by this example, we can see that we will reach different states again and again and through different paths. So in this case, um, suppose these were the two numbers that we're trying to find. So in the first case, we put 2 and then we put 5 in position 1. Then for different paths, we put 5 first and then 2. So and suppose the tight in both of those cases was 0. So basically, suppose the number was this and the upper range was 9, 7, 8, 9. So while choosing 2, we stayed under the limit. We're not in any like tightness bound. For this also, we chose 5. So we're both, and for both these numbers, we're under that tight bound. So it'll be 0, right? In this case also it'll be 0. In this case also it'll be 0. The sum, so we reach position 1 by choosing 2 first and then 5. And then in this case, we chose 5 second and 2 second in this case. So we reach 170, this recursive relation. So in both these cases, we reach the same state. So if you calculate it for one, we can surely use it again for the second state. So we don't need to like again calculate this state because we already have it cached in somewhere and we can reuse it. Okay, to summarize again, the idea is you have an upper range, right? This is the upper range. You're supposed to find sum of digits of all the numbers under this upper range, uh, whose digit sum lie between two values, low and up. And if this is the case, we add it to the count. So if there is a number, we'll try to generate all numbers with this recursive relation, placing different digits in each position and making sure they stay under the upper range and calculate this sum. If it lies between this, then we are good. We add it to the count. So this is the idea. And if the ranges given are upper and lower, in this case, so what we do is find all the numbers starting like under this range, which have this sum. So our answer would look like count upper, which is this number, and we pass it something called sorry. So this would be count upper will be solve starting at position 0. Sum is 0. If it is tight bound, so in the first case it will be. So in the when you start generating the string in the first position, you always have to stay under the first digit of the upper range. So this will be 1 and count lower. So these will give you all the numbers from 0 to upper range, which have a digit sum between L and D, right? And for count, similarly with count lower, you do the same thing. You just pass the lower number instead of the upper, and in this case, you pass the upper number. And your answer should then be count of upper minus count of lower. So all the numbers which are in this 0 to U range minus all the numbers which are in 0 to L range. So this is the general idea. So I'll just walk through the code now to make it to clarify it better, I guess. Okay, so again, I won't take much time here. So okay, this is the solution for this problem. Okay, so never mind the subtract one. So what I'm doing here is because it's a uh, the upper range could be large, they've given it as a string, the number as a string. So if I try to do -1, it'll overflow. So I'm using subtract one to. Okay, so one more thing. I think I explained it wrong. So it won't be it won't be solve of upper minus solve of lower. It should be, this is wrong. So this is wrong. It should be solve of upper minus all the numbers less than L. So this is our answer. So this is our answer, not solve of U minus solve of L, but solve of U minus solve of L minus 1. So because you're supposed to consider the lower range as well, that's inclusive. So this is gonna be our answer. So let's go through what this solution is doing. So you have a solve function. Never mind the base case still for the time being. Okay. So and let's forget that we are caching it somewhere. Let's just try to find the recursive solution. Okay, so we have this tightness bound. I've used edge here. So if it stays in that edge, you can use anything from 0 to 9. And if it if the number is still tight, you can use anything within that digit, till that digit of the upper range. So when you start from position 0, you're gonna check if edge equal to 1. So in the first case, it is, right? So you if it is the case, you can only use numbers from the limit will be whatever the digit is at that position in the upper range. So we have this range also passed along to the solve function, and at position 0 we're checking if what that number is. So in their example, let's take something bigger. So if the upper range was uh, 453. Okay, this was the upper range. Okay. So in the first case, when we passed it with edge equal to 1, we can only go up from 0 to 5. So this is what we're doing. We're trying to see what the edge is in this case. So you can only go from 0 to 5. Anything over this is you're crossing the upper range, right? So and if it was 0, if it was 0, you can, if this edge was 0, so suppose for the first, so you're trying to generate your number, and in the first position you use 2. So your edge will be now 0, right? For position k plus 1. So from in the second position, you can use anything from 0 to 9, and you're not bound by using a digit from 0 to just 3. Because in the more significant bit, you've used something which is already lesser than it. So any number after it will be smaller, right? So that's what we're doing here. So we're trying to like place all the digits from 0 to edge, and then using that to make a recursive call for position k plus 1, and using that ith digit. Okay, so if you use 1, the sum is going to increase from 0 to 0 plus 1. And if you use so this tight, what is this tight doing? So I'm checking if I used, if the number I'm using equal to edge. So in my case, the edge was till, suppose for the second digit, 5, right? So if I use 5 and already the edge was 1. So from the previous recursive call, the edge was already there. So you are bound to use something lesser, and you use the edge again in this case. So the next call to position k plus 1 will use the same 1 edge, because the number is going to be greater than the upper range. So this is what I'm doing. I'm just moving to position k plus 1, adding that digit, and making sure I'm under that range with this tight variable. And the recursive case again. So if at any time sum goes over this upper range of whatever they were asking, so this max sum, so that is not a valid case, because you're already over that. The digit sum is already over that max. So you can just return 0 in that case. So anything you use after that doesn't matter. Now, if k is range.length, so whatever the number was, you've reached the end of it. Now you'll just check if sum is greater than DL and less than DR, you return 1. Otherwise, you return 0 if it lies anywhere outside that range. So, yeah, and now memorizing it is going to be easy, because you're just going to use, you can see K changes in this case, our position changes, our sum changes, and our tightness bound changes. So these are the three variables we need to work with. And we're just going to generate a key. If it's already present, you just return the count from that. Otherwise, you solve it and put it in that uh, map. And let me check if I'm missing something. Yeah, okay. So again, so this solution, we mentioned that the brute force way was n log n, O of n log n time complexity. How much will this be? So this k is the length, the number, or in this case, our upper range, right? Or the lower range. So this can be what? Log n. This is log n. What is the sum? The maximum sum that you can have is 9 into uh, the number of digits, which is again log n, plus e, which can take the value 0 or 1 if it's tight or not tight. So 2. So our solution would then be log of n square, which is much better than what we had earlier with brute force, which was n log n, right? So yeah, and these type of problems where you see a huge range, you can make be pretty sure about this that you need to use digit DP to make this work and just memorize the different states again and again. Um, yeah, so that's pretty much it.